Okay, same topic. Operational amplifier. This is lesson number 2. This is the symbol for operational amplifier. This is positive supply voltage. This is negative supply voltage. This is non-inverted input terminal. And this is inverted. And this is output terminal. We have done 5 properties. Number 1, the impedance of these two these two input terminal must be infinity to stop the current entering or leaving the op amp through these terminals. Number 2, impedance of the output terminal must be 0, because when this output terminal is connected with any electric device, it requires current. So due to output voltage, there must be current according to Ohm's law, V is equal to IR. But this is electronics, no current required for it. Number 3, open loop gain. Open loop mean a circuit in which no current. Open loop gain mean advantage, electronic advantage, which is output voltage over input voltage, must be infinity. Number 4, the range of the input voltages must be infinity, mean the bandwidth of the input voltages must be infinity. And number 5, the slew rate, mean the response of this operational amplifier for its function, for its working, must be infinity. So these are 5 properties of ideal operational amplifier. But practically, number 1, impedance of these two input terminals lies between 10 power 6 to 10 power 12 ohm. We have done in the previous lecture. And number 2, impedance of the output terminal is 10 power 2 ohm, mean 100 ohm. And number 3, practically, open loop gain is not infinity. For the direct voltage input, it is 10 power 5. And number 4, bandwidth of the input voltage is not infinity. It is still undefined because gradually improving day by day. And number 5, its slew rate is not infinity, mean its delay rate is not 0. It delays for 1 microsecond when input voltage fluctuates for 10 volt. If there's a fluctuation of 10 volt, then it delays for 1 microsecond. So these are the properties for practical and ideal operational amplifier, as we have done in the previous lecture. Now, do remember, number 1, this output voltage is directly proportional to difference of the input. Larger the difference between two inputs, greater the output. Number 2, this output maximum can be plus minus supply voltage. If it's coming output voltage greater than supply voltage, then the op amp is called saturated, mean faulty. And number 3, when non-inverted input terminal voltage is greater than inverted input terminal voltage, then the polarity of the output voltage will be positive. And number 4, if non-inverted input voltage smaller than the inverted input voltage, then the polarity of the output voltage will be negative. So these 4 points are important, 1, 2, and 3. Now, the point number 1, which is V out directly proportional to difference of the input. So we can write some constant here. Suppose A naught, difference of the input. So output voltage divided by difference of the input voltage is equal to A naught. Look, ratio between output and in voltage is called gain. So this A naught is called gain. So this is the open loop gain. So it has no unit here. Now, for example, the graph between difference of the input voltage in volt and the output voltage at the y-axis is drawn. Both are directly proportional, but when output voltage becomes equal to supply voltage, then it is saturated. So this horizontal line is saturated, and the gradient of this line is gain A naught, and this line has zero gain because it is saturated. Okay, now sometimes this operational amplifier is used like this. One of the input is 0, meaning it's connected with the earth, and here is the practical just one input. This is the supply voltage positive, this is supply voltage negative. Then the graph between difference of the input mean just input, because the difference of any number with 0 will remain the same, right? For example, it's a 5 volt is 0, so answer will be 5, and this is output. So the graph will be straight line passing through the region, but when output becomes equal to supply, it is saturated, no gradient, 0 answer. Now, in electronics, a battery is required which delivers only voltage, not current. So the battery which delivers voltage, not current, because electronics work on voltage, not on the current. So for this purpose, we will take 2 batteries. Both are connected in series. This is positive terminal, negative, this positive, negative. So both are connected in series. Now this battery is connected with a switch. It is connected with the ammeter. It is connected with any electric device. Suppose this is the lamp. And then circuit is completed. And voltmeter is connected parallel to this lamp. Now when switch S is closed, this ammeter will give you reading, voltmeter will give you reading, and the bulb is on. So this is not required in the electronics because it is giving you the current. So this is not the proper battery required in the electronics. So we have to make some change in it. We will connect this common lead of 2 batteries with the earth. When this common lead is connected with the earth, so this negative becomes 0, this positive becomes 0, means 0 potential, mean it becomes dead, it is dead. Now circuit is incomplete now, no current, because there is no current circuit, closed circuit. This bulb is off now, but the voltage is still there. Like as we have done, these are the two plates, one connected with the positive, other connected with the negative. So there is a voltage. So this is a situation. Look, these are the two battery, but we are taking positive from this A battery and the negative from this B battery. So this combination with earth connection is called dual split battery. These are the two batteries, but both are splitted into two, positive from one battery and the negative from the other battery. So these types of the batteries are required for the electronics. Dual split batteries. No current, but only voltage is delivered by them. So do remember, in electronics, we use dual split batteries. Now, the application of op-amp. For example, this is the first application. So first, we'll draw here the dual split batteries. We have to split it. We will connect this with the earth. So this is ineffective, this is ineffective, so this is positive, this is a negative. Now, we have to give supply. We have to supply to the op-amp. So positive supply from this side of the battery to switch it on, and the negative supply from this. So do remember, here is no junction. For the junction, we have to draw here a dot. So mean wires are not connected. They are just crossing each other. So this side is the positive supply, this side is the negative supply. So this operational amplifier is switched on just, but we have to give it 2 input voltage to get the output. For the inputs, we will draw here a potential divider. In AS, we have done when two resistors at least connected in series, then the circuit is called potential divider. Look, this is the junction here. This is junction. Now, the value of this is R. This R mean both are the same value. And here, suppose this is 12-volt battery, 12-volt battery. So 12-volt supply positive, 12-volt here, but here 0-volt. So this 12-volt equally divided 6-volt here, 6-volt here. For the input, we will connect non-inverted terminal of the op-amp with this wire here. And one important thing, voltage across the resistor, which is connected with the earth, is supplied as input. तो ऑपरेशनल एम्पलीफायर को कौन सी वोल्टेज इनपुट जाएगी? Voltage across the resistor, which is connected with the earth. So this is connected with the earth. So voltage across it is actually the non-inverted input voltage, because this resistor is connected with earth. Very, very important. So at this instant, the voltage input at this terminal, non-inverted, is 6. And similarly, we will draw here another potential divider. This is resistor. And here is any variable resistor. For example, this is LDR. This is fixed resistor. This is LDR. Now the voltage at this end is 12, at this end 0. This is a potential divider, but this potential divider is variable because with the change in the intensity of the light, voltage across the LDR and the fixed resistor change. Now, this wire is connected here as inverted input. And this is output terminal for the output voltage indicator, either connect voltmeter or LED. Suppose this is the first LED light emitting diode and its color is green. And the other LED is connected in the reverse direction because sometimes voltage positive, sometimes negative. So these are the two LEDs. Now look, in the darkness, if the intensity of the light in the surrounding is minimum, then the resistance of the LDR is maximum. When the resistance of the LDR is maximum, so there will be a maximum voltage across the LDR rise as compared to this fixed resistor. Suppose 10 volt here and just 2 volt here, and the total voltage will remain 2. So 10 volt and 2 volt. Now look at this. This resistor LDR is connected with earth. So its voltage is going to this input terminal, which is inverting. Now this is 6 and this is 12 in magnitude. And we have done when non-inverted is smaller than inverted, then the polarity of the output is negative. So due to this difference, here the negative output, and due to negative output voltage, this is positive terminal, this a negative, this a negative positive. So this green LED is reversed bias because it's positive terminal connected with the negative. So no current through this green LED, but look, negative connected with the negative. So it becomes forward bias, current flows through it. So the red goes on. Mean when there is a darkness in the surrounding, the darkness is indicated by the red LED. Now suppose sun shines, light intensity increases, there is a brightness in the surrounding. In bright light, resistance of the LDR decreases. When resistance decreases of the LDR, its voltage decreases. For example, instead of 10 here, this is 10. Instead of 10 here, instead of this 2 here, suppose 2 volt here and 10 volt here. So when here, 2 volt, this is fixed, so it remains 6. So in this situation, this 6 is greater than 2, mean non-inverted, greater than inverted. So it means output polarity is positive. So this becomes positive. Now this is reverse bias. This becomes forward bias because positive connected with the positive. So current flows through it and green goes on. When there's a darkness, red on. When there's a brightness, right, green on. For high intensity of the light in the surrounding, this is the indicator. For the low intensity of the light, even darkness, this is the indicator, okay? So when there is a darkness, here voltage was 10, here voltage was 2, so 10 volt here and 6 here, so 10 greater, so negative output, red goes on. But in the brightness, here voltage less 2, here 10, total 10. So when it becomes 10, this non-inverted greater than inverted. So the instead of red, green goes on. So this is the application of this operational amplifier, one of the application, and this is called light intensity comparator circuit. light intensity comparator circuit. It compares the intensity of the light. Okay, now if the position of LDR and the fixed resistor are exchanged, mean fixed resistor here and LDR here, suppose, then what will happen? The operational will be reverse. So initially for the darkness, red goes on. Now for this change, for the darkness, green goes on. Initially for the brightness, green goes on, but for this change, for the brightness, red goes on. So this is the difference. And the next, if this LDR is replaced with thermistor, then it compares temperature high and low. When the temperature will be high, the resistance of the thermistor will be low, right? So this green goes on. And when there's a darkness, resistance is high. So this inverted becomes high. So negative output, so red goes on. And similarly, when thermistor is here and the fixed resistor here, they are replaced with, they are exchanged with each other. Then for the high temperature, red will go on, and for the low temperature, right, green will go on. So this circuit for LDR is called light intensity comparator. But when thermistor is used instead of the LDR, this is temperature comparator circuit, mean it compares temperature. And this temperature comparator circuit is used in ovens. When low temperature, LED green. When the oven is hot, according to the required temperature, then it is red. So it compares the temperature.